In the previous section, we looked at partial derivatives, and we're going to continue on finding derivatives of multivariable functions in this section, 14.5. But in this section, what we want to focus on is using the chain rule for multivariable functions. So let's look at this theorem. Let's say we have this function z, and z is written in terms of the variables x and y. However, let's suppose that x and y are both functions of another variable t. So if I wanted to find the derivative of z with respect to t, I have to first use the chain rule to find the derivative of z with respect to x, multiply it by the derivative of x with respect to t, and then add it to the derivative of z with respect to y times the derivative of y with respect to t. So here, z is written in terms of two variables, x and y, but we're not trying to find the derivative of z with respect to x or the derivative of z with respect to y. We want to find the derivative of z with respect to t. So the dependent variable that we're looking at is our z function, and the independent variable is t. So x and y are what we call intermediate variables. So this is a lot of words, and it kind of doesn't have a meaning until we look at a tree diagram. So I'm going to illustrate the chain rule with a tree diagram. So we have our function z. Z is written in terms of two variables, x and y. So I'm going to write two branches. At the end of one branch, I have x. At the end of the other branch, I have y. However, my function x is written in terms of a variable t, and my function y is written in terms of a variable t. So whenever you take the derivative of a function of two or more variables, it's the partial derivative. So notice if I take the derivative of z with respect to x, it's a partial derivative of z with respect to the variable x. If I take the derivative of z with respect to y, it's the partial derivative of z with respect to y, because z is written in terms of two variables x and y. However, if I take the derivative of x with respect to t, since the t is the only variable for my function x, this is our usual derivative dx dt from single variable calculus. And if I take the derivative of y with respect to t, again, it's single variable calculus dy dt. So if I want to find the derivative, the derivative of z with respect to t, and this is not a partial derivative, it's a derivative because this is the single variable t, then I have to follow down both of these branches. I have to first take the derivative of z with respect to x and the derivative of x with respect to t. And that would be this multiplication of the partial derivative of z with respect to x times dx dt. However, I have another branch with my variable t, so I need to add the other branch, which would be the partial derivative of z with respect to y times dy dt. And that's where that formula comes from, the chain rule used when you have a function z of two variables. However, each one of those variables are also a function of another variable, t. And this idea, this chain rule, can be extended to any function with as many variables as you want. So let's look at this first example one. And let's say we have this function w. It's written in terms of x, y, and z. However, x is a function of t, y is a function of t, and z is a function of t. So we're going to draw a tree diagram and we're going to find dw dt. So we start out with our w, and it's written in terms of x, y, and z. So we break this up into three branches, x, y, and z. X is a function of t, y is a function of t, z is a function of t. So if I go down the branches, if I want to take the derivative of w with respect to x, it would be the partial derivative of w with respect to x. The derivative of x with respect to t is simply dx dt. W with respect to y is partial. Y with respect to t is single variable calculus. W with respect to t is partial, or z, sorry. And then z with respect to t is dz dt. So I have my tree diagram, and I want to find the derivative of w with respect to the variable t. So my variable t is at the end of three branches, so I'm going to need three pieces to my chain rule. I need wx, xt, wx, xt, wy, yt, wz, zt. That would be the partial of w with respect to x times dx dt plus the next branch, partial w with respect to y, dy dt, plus third branch, the partial of w with respect to z times dz dt. So these tree diagrams are very powerful. Again, we can use them to find derivatives for any function with any finite number of variables. So let's apply this chain rule to some functions that are defined. In example 2, we have z equal to x squared plus y squared plus 5. So z is a function of x and y. However, x is equal to sine of t and y is equal to 2 cosine of t. So sine x is a function of t and y is a function of t. We're supposed to find dz dt and evaluate it at t equal to pi over 4. I could draw myself a little diagram if I'm unsure of how to find the derivative. So z equation, the variables written are x and y. If I look at x, the variable is t. If I look at the function y, the variable is t. So I can see that to find the derivative of z with respect to t, and here I have my t values at the end of two branches, so I need two pieces. Follow along the branch, we have the partial derivative of z with respect to x times dx dt plus partial derivative of z with respect to y times dy dt. So why don't we use these functions that we have and compute this? Now you can use a notation that you had from calculus in the past. dz dt is simply z prime of t. So you're free to use any of the notations that apply. The partial derivative of z with respect to x is simply 2x times dx dt is cosine of t plus partial of z with respect to y is 2y times dy dt is going to be negative 2 cosine t, or negative 2 sine t, sorry. I have a problem. I was trying to find the derivative with respect to t. In my expression, I still have x's and y's. So I'm going to need to substitute x equal to sine of t and y equal to 2 cosine of t. So this becomes 2 sine cosine, sine t cosine of t. And now I have 2 times 2, that's a negative 4. Y is 2 cosine times 2 cosine t, and then sine t. Could have just written negative 8. So look at this. I have 2 sine cosine minus 8 sine cosine. It's going to end up being negative 6 sine t cosine t. And I could actually write it in a more efficient way by remembering that 2 sine cosine is sine of 2t. But I'm going to stop right here. And then now I need to figure out the derivative at a t value of pi over 4. So that's negative 6. Sine of pi over 4 is square root 2 over 2. Cosine of pi over 4 is square root 2 over 2. So putting all this together, I get negative 3. Okay, let's try another example. Example 3. I have my function w. It looks like it's written in terms of x, y, and z, 3 variables. X is a function of t, y is a function of t, and z is also a function of t. We're supposed to find dw dt. If you wish, you can draw a diagram, but you don't have to. If you're okay with realizing, oops, and that's not supposed to be partial. Sorry, I'm on autopilot a lot, and I do this a lot. It's not a partial derivative. So notice that w is written in terms of x, y, z. So I'm going to have 3 branches. I'm going to have the partial of w with respect to x times dx dt, plus the next branch would be the partial of w with respect to y, dy dt, plus third branch would be the partial of w with respect to z, dz dt. Again, you can also draw the diagram. So the derivative of w with respect to t, the partial of w with respect to x would be y minus z times dx dt is negative sine t plus partial of w with respect to y looks like x plus z, and then dy dt is 1 over t plus partial of w with respect to z is y minus x. And then dz dt is e to the t. So let me go ahead and u. Again, I'm trying to find the derivative of w with respect to t, and I have y's and z's and x's in here. So I have to substitute for the y, the x, the z. y is natural log of t, so I get natural log of t minus z is e to the t, and then that's going to be multiplied by negative sine of t plus x is cosine of t plus z is e to the t, and that's multiplied by 1 over t plus y is natural log of t minus x, which is cosine of t, and that's times e to the t. I'm not going to bother to clean this up. I'm just going to stop here. Of course, on my math lab, they would probably want you to simplify this, but I'm okay with stopping right there. All right, let's go ahead and move on. What if we have two independent variables? So let's just say that z is a function of x and y. However, x and y are functions of not just t, they're functions of two variables, s and t. Well, in this case, working down the tree, and I'll go ahead and look at this tree diagram, z is a function of x and y. X is a function of s and t. Y is a function of s and t. So if I were to find the partial derivative of z with respect to x, and notice it's a partial derivative, and the reason why is because looking at this tree diagram, I don't want that pen, I want the thinner one. Looking at the ends of the branches, the ends are not just the variable s, the ends are the variable s and the variable t. So to figure out the partial derivative of z with respect to s, we just follow the branches from z to s. So it would be the partial derivative of z with respect to x times the partial derivative of x with respect to s, plus the partial derivative of z with respect to y times the partial derivative of y with respect to s. And that would be the partial derivative of z with respect to s. Now let's look at this other diagram. Let's say that we wanted to find the partial derivative of z with respect to the variable t. So as you notice, there are two branches that lead to the variable t. I would have to take the partial of z with respect to x times the partial of x with respect to t, plus the partial of z with respect to y times the partial of y with respect to t. So that's what's in these boxes below. You can see how powerful these diagrams are. You can use them again for any function of any finite number of variables. Example 4, we have z. It's written in terms of x and y. So z is written in terms of two variables. X is written in terms of two variables s and t. Y is written in two variables s and t. So if I wanted to find the partial of z with respect to x and the partial of z with respect to t, first let's look at the partial derivative of z with respect to s. Again, you can look at the diagram above. It follows that model. We're going to have the partial derivative of z with respect to x times the partial derivative of x with respect to s, plus partial of z with respect to y times the partial derivative of y with respect to s. That would be simply negative sine of x times 1 plus partial of z with respect to y would be 2 cosine 2y. As we're using the chain rule there. And then negative 1 would be partial of y with respect to s. The problem is I have an x and a y that I need to substitute for. So I don't really need this 1 here. It's not going to change my product. This would be a negative sine of x, but x is equal to s minus t. And then this is times a negative 1, so this is going to be a minus 2 cosine of 2. Y is t minus s. And I have to stop there. I actually can't go any further. I cannot replace my s with some t value. So this is as far as I can go, which would give me the partial of z with respect to s. Now remember, we have some other notation we can use when we're finding derivatives. So let's find the partial derivative of z with respect to t, which would be the partial of z with respect to x times the partial of x with respect to t plus partial of z with respect to y times the partial derivative of y with respect to t. And that would be equal to negative sine x times partial derivative of x with respect to t would be negative 1, so times negative 1, plus the partial derivative of z with respect to y is going to be negative 2 cosine, or positive 2 cosine y of 2y. Oh, can't speak today. Times 1. And then substituting for the x, that would be the s minus t. So I have a negative sign times a negative 1. So this becomes a positive sine of s minus t plus 2 cosine of 2 times t minus s. So this does look a little weird. It looks like it's the t minus s is separate from the cosine function, so you might want to put another set of parentheses here or clean it up and write this as 2 cosine of distribute the 2 and simply 2t minus 2s. So that looks a lot nicer. And then this would be partial of z with respect to t. These are kind of fun. So here's some other cases. Now, there are infinitely many types of functions and diagrams that we can draw, but let's just look at some more for fun. Let's say that we have this function w is written in terms of 3 variables, x, y, and z. So I break w into 3 branches, x, y, and z. And let's say that x is a function of s and t. So x breaks off into s, t. Y is a function of s and t. So y breaks off into st. And z is a function of st. So you can see that what if s were a function of some u and v? Or t was a function of some u and v, then we can keep continuing on with our branches. So here is our partial derivatives if we follow down the branches. Now, if I wanted to find the partial derivative of w with respect to x, remember it's a partial derivative because s is not the only variable at the ends of these branches. There's also a t, so it's still partial. If x was only a function of s, y was only a function of s, and z was only a function of x, then it would not be partial derivatives. It would be just our regular dw ds. Here's a fun case. Let's say that w is a function of only one variable z. So I only need one branch from w to z. However, z is a function of two variables, x and y. So we break z off into two branches. And then x is a function of one variable t, y is a function of one variable t. So you notice down our diagram, since w only splits off into one variable, it's our usual derivative dw dz. However, z is a function of both x and y, so those are partial derivatives. But x is only a function of t, y is only a function of single variable t, so that's dx dt, dy dt. And then you can go ahead and look at dw dt. Let's do another example. Example 5, w is written in terms of an x, a y, and a z, so three variables. X is written in terms of two variables, s and t, y in terms of two variables, s and t, and z in terms of two variables, s and t. So if we go back up, it looks like this top diagram. W is breaking off into three variables, x, y, and z are breaking off into two variables. So we are supposed to find the partial derivative of w with respect to t. So the partial derivative of w with respect to t will be equal to the partial derivative of w with respect to x times dx, or partial derivative of x with respect to t, plus partial of w with respect to y times partial of y with respect to t, plus partial of w with respect to z times the partial of z with respect to t. And that's going to be y minus 1 times 2 plus x plus z times negative 1 plus w with respect to z, that's just y. Y with respect to t, or, oh, that looks like negative 1. Oh, sorry, that's z with respect to t. I'm terrible. Z with respect to t is simply s. And now I'm going to replace my y value with s minus t. So this becomes 2 times s minus t minus 1. And this negative 1 I'm going to put out in front as a negative. Replace my x and my z, which would give me s plus 2t plus st. Let's see, plus y is s minus t n times s. All right. So that would be the partial of w with respect to t. Now we're supposed to evaluate this when s is 1 and t is 1. If I want, I can clean this up a bit. It seems like I have a lot of like terms. Let's see, so 2s minus 2t minus 2 minus s minus 2t minus st plus s squared minus st, and then combining like terms and rearranging. It looks like I just have one s. I have minus 4t minus 2st plus s squared minus 2. All right. So if I was going to evaluate the partial of w with respect to t at s is equal to 1, t is equal to 1, I could write it this way: s equal to 1, t equal to 1. And then that's going to be equal to 1 minus 4 minus 2 plus 1 minus 2, or negative 6. So another notation you could use when you're evaluating would be the partial of w with respect to t, and use an ordered pair 1 comma 1 for st, and typically ordered pairs are written in alphabetical order, so the s value comes first, the t value comes second. Example 6, we have a function w. It's written in terms of 3 variables, x, y, z. X is written in terms of 2 variables, s and t. Y is written in terms of 2 variables, r and s. And z is written in terms of a single variable, t. So we're going to use a tree diagram to find the partial of w with respect to t. Okay. So first of all, w is written in terms of x, y, z. X is written in terms of s and t. Y is written in terms of r and s. Z is written in terms of just the single variable t. So this is what our tree diagram looks like. And we're supposed to be finding the partial of w with respect to t, which would be the end of 2 branches. So if I follow down, I have w with respect to x would be partial. X with respect to t would be partial. And then the other branch would be w with respect to z, partial. Z with respect to t, single variable calculus, so dz dt. The partial of w with respect to t is going to be the partial of w with respect to x times the partial derivative of x with respect to t, plus the partial of w with respect to z times dz dt. Okay, so you can see how powerful these diagrams are. So let's pause for a second. And look at implicit differentiation. So in previous sections, we talked about functions written in explicit form and implicit form. So if you have a function set equal to 0, that would be our implicit form. So let's say that we have some function f, and it's written in terms of the variables x and y. Let's suppose further that y is a function of x. Provided the partial of f with respect to y is not equal to 0, when we find the derivative of y with respect to x, it's going to be the negative partial of f with respect to x divided by the partial of f with respect to y. We're going to verify this theorem by first drawing a diagram. Notice that my function f is written in terms of two variables, x and y. My function y is written in terms of the variable x. So this is what my tree looks like. So if I go from f to x, it's partial of f with respect to x, and then f to y would be the partial of f with respect to y. Y to x is single variable, so dy dx. So let's go back to this function that we have, f of xy equal to 0. And now I'm going to verify this theorem. I'm going to take the derivative with respect to the variable x of f of xy. So I'm going to take the derivative on both sides. So the derivative with respect to x of our function f, well, that's simply the derivative of f with respect to x. And then the derivative of 0 is 0. Okay, I'm going to stop there. And then I'm going to also look at the tree diagram to figure out what the derivative of f with respect to x would look like. So notice that x is at the end of two branches. So I have to follow these branches. I first have the partial derivative of f with respect to x plus, and then we follow down our second branch, partial of f with respect to y times dy dx. Okay, so something to note is, remember, we've already shown that df over dx is equal to 0. So I can substitute 0. This is equal to the partial derivative of f with respect to x plus partial of f with respect to y times dy dx. To verify the theorem, all I have to do is solve this equation for dy dx. So I'm going to subtract the partial of f with respect to x. And here I'm going to rewrite this first using the notation from this theorem. Partial of f with respect to x, we can write that as f sub x. Partial of x with respect to y, that could be written as f sub y. So I would simply subtract the partial of f with respect to x from both sides, and then divide both sides by the partial of f with respect to y to get my dy dx. And that verifies the theorem for implicit differentiation. In example 8, we're going to use the theorem that we just verified to find the derivative for this function. And then we're going to verify our derivative by going back to calculus 1 and using implicit differentiation. If I were to use the theorem, the derivative of y with respect to x is simply negative. Partial with respect to x would be 4x to the third plus 5y to the third over the partial with respect to y is 15x y squared. And that's it. So let's verify by using implicit differentiation. So we're taking this equation and we're trying to find the derivative of y with respect to x. So x to the fourth becomes 4x to the third. The problem with 5xy to the third is we have to use the product rule. It's 5x times y to the third. So by the product rule, we take the derivative of 5x is just 5. The y to the third stays the same. Plus, keep the 5x. The derivative of y to the third is 3y squared, but it's implicit differentiation, and we're treating y as if it were the function. So this would be our dy dx. And then that would be equal to 0. Let me clean this up. I have 4x to the third plus 5y to the third plus 15xy squared times dy dx equal to 0. Well, I need to solve for dy dx. I could subtract the 15xy squared dy dx from both sides. And then I would simply divide everything by the negative 15xy squared. So I get the same thing, same derivative as I did when I used the theorem. However, going back to Calc 1 using implicit differentiation, it takes a very long time. So it's easier just to use the theorem if applicable. And now we can also use implicit differentiation with 3 variables and even 4 variables or 5 variables. So let's say we have this function x, y, and z equal to 0, and notice that z is a function of x and y. So again, this is in implicit form. Then to find the partial derivative of z with respect to x, it's going to be the negative partial of x over partial of z, and then z with respect to y would be negative partial y over partial with respect to z. In example 9, we want to find the partial derivative of z with respect to x and the partial derivative of z with respect to y for this given function. Our partial derivative of z with respect to x is going to be negative cosine of x over y squared minus 3z squared. And the partial derivative of z I'm sorry, didn't realize I paused the video. And then the partial derivative of z with respect to x. I don't like the negative in front and the negative in bottom, so I can write it in a simpler form, cosine of x over 3z squared minus y squared. But you don't have to go that far. So the partial derivative of z with respect to y is negative. In the numerator, I have 2yz over denominator y squared minus 3z squared. Or I could write this in a nicer form by dropping the negative into the denominator to get 3z squared minus y squared. And that's it for this section.